Hi class, this video is going to help with section 8.1, and this is over basic probability. Okay, so let's start with what is probability? Most of you have seen it before by now, but it's just how likely it is for something to happen. So the numbers go from 0 to 1, and in a percent form, they go from 0 to 100%, which you should know, 0.8 is 80%. So those are the same thing, they're just in different forms. So if I say it's 80% likely that it's going to rain today, it's pretty likely it's going to rain. If I say 0% chance of snow, which is never in Wyoming, then that means it's not going to snow. This is zero likely, not going to happen at all. If there's 100% chance that I'm going to record 3 videos today, then it's going to happen, right? So probability 0 to 1 or 0 to 100%. So imperial or experimental probability, you actually perform an experiment and find the probability. Okay, so answers are different for you or me. So if I take a coin and I flip it and I see how many heads, how many tails, and I base my probability off of my coin I flipped, then that's an experiment. Okay? That's different than theoretical. That's what's expected, what should happen. So I know when I flip a coin, it's a half a chance to get a heads or tails. But if I do an experiment, that may not happen. If I do the experiment enough, then it should go to the theoretical probability. Then it'll lean towards that. Okay, sample space is the first thing you kind of want to find every time. It's like all of your possibilities that you could have. So if I have a coin that I'm flipping, I have 2 possibilities, heads, tails. So that's my sample space. Sample space is the number 2, and it's heads and tails. Okay, so you could have to list them and just say the number. If I have a deck of cards, what's my sample space? 52 cards, right? I could list them all, but no thanks. I just say there's 52 cards in the sample space. Why is that important? Because that's going to be our denominator of our probability. So let's look at a couple things real quick. So move my paper up a little bit. The probability of an event E. So we'll see this notation, big capital P for probability. Little e is going to be for event. So this first example, I flip a coin 2 times. What is my sample space? So I didn't just flip it once, I flipped it twice. So I drew a tree diagram because those are really handy in a lot of probabilities. So I would have my first 2 choices as heads and tails. On the second flip, I would have heads or tails also, or heads or tails also. So these are my options. I could have had head, 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 tail, tail, head, or tail, tail. That's my sample space. So we have the number 4 in our sample space. And our sample space is our denominator, and then our numerator will be that event. So for example, if I wanted to know the probability of getting at least 1 head, at least 1 heads, then I would have 1, 2, 3 out of 4. So the probability is 3/4, 0.75, 75%, any of those ways you want to write that. Okay, so please use a tree diagram. It's one of the, a great way to see your sample space and your total options. Now, it's not so great if you are flipping a coin 50 times, then we have to have other options. So number 2 here, what if I have a spinner? What's the probability of rolling an even number? So probability of an even number is, so here's my spinner. What is the probability of getting an even number? Well, there's 1, 2, 3, 4 even numbers, 8 total. So it's 4 eighths or 1/2 or 50%. So we automatically got our sample space. So I think a lot of your problems will be like, how many possibilities for this event? What's your sample space? What's the probability? So we could be looking at flipping a coin, a spinner, a deck of cards always kind of throws people. We'll do some deck of cards. Okay, let's look at what if I have 43 cans of Coke, 22 orange sodas, 33 ginger ales, and 2 root beers in my fridge? That's a lot of soda. I don't even drink soda. I might be asked a question with the word or in there. What is the probability of orange or ginger soda being chosen out of that fridge? So you go over, you add orange and ginger together. 33 and 22 makes 55. And then you add up all of them because our sample space is everything, which is 100. So it's 55 out of 100, which is 55%, and or 11/20ths if you reduce the fraction. Okay. So you could be given something, you could be asked the word or. Or means add your possibilities. This or this. Okay, so let's look at, let me look at this other one that I have with a deck of cards, just because they tend, especially if you don't play cards, they tend to kind of mess people up some. So I'm going to bounce over here and show a couple examples. I don't know what number I'm on. They renumbered now. Okay, so I have a deck of cards. There's 52 cards in a deck. There's 4 suits, right? 2 blacks, 2 reds. Each suit has 13 cards. Okay, so what is the probability of getting a red jack? How many red jacks are there? 2. So the probability is 2 out of 52. If you want to reduce, you can reduce. Okay. The ace of spades. Well, spades is very specific. The ace is very specific. There's 1 ace of spades, so there's 1 out of 52. Probability of a 6 or a 7, same probability. There are 4 suits. Each suit has a 7 or 6. So there's 4 out of 52, or 1/13 is the probability of getting a specific card. Okay. Now we're getting into some or. Number 5. What is the probability of getting a 5 of hearts or a 5 of spades? So we have the word or, so we're going to add the 2 possibilities. So there's 1 5 of hearts, there's 1 5 of spades. So then we add those, there's only 2, and we get 2 out of 52. What is the probability of not getting a red? 6. Oh, I didn't catch the red 6. Well, there's 2 red 6s, so there's 50 that aren't, so 50 out of 52. I thought they got harder. Face cards. Ooh, that's way harder then. I'm like, I know they get harder. Okay, an experiment consisting of dealing 4 cards with a standard deck of 52. So maybe I should move it to where you can read it. There we go. So an experiment consists of dealing 4 cards from a deck of 52 cards. So getting harder. I'm going to deal you out 4 cards, right? We still have 52. Let's look at this first one here. What is the probability that you just got 4 kings? Man, that would win you some serious money in Vegas. What is that probability? Ooh, well, we're going to have to go back to combinations and permutations. So give me a second here. They kind of labeled this a little different. There are 4 kings and 4, so it's basically one way for you to get that. But then we have to do, I don't love, why didn't they show, oh, they did show that. Okay, so if I have 52 cards and I'm picking 4, they write this a little different. Usually the 52's on this side. This is the way you type it into a TI-89. So this is the way they have it. But I would put that into my calculator and get that combination because it's not a permutation because order doesn't matter. I'm just picking 4 cards from the deck. So I'm going to go 52, and then go to math and go over to probability down to C, and I want to pick 4, and that's where they get this number here. You don't have to use the formula, or you can, totally up to you. But this will be our denominator on most of our problems because that's how many ways I can get 4 cards. Crazy how many different ways I can dish up 52 cards. Okay, so there's only one way to get all kings. So again, it's a combination 4, choose 4, and I would then have 1 out of this. So look, if I divide those 0.000, it's almost 0% chance that you get 4 kings. That's why you'd win a lot of money. What about 3 kings and a queen? Well, then what we do, we still have our denominator the same, but we'll do 4, choose 3 combination, and we'll do 4, choose 1, and then we're going to times those together. The word and, we times, or we add. Okay, and I want to get this one and this one. That's way harder than this one or this one. A lot less options. So we're going to times these together, and we would get 16 total. There's 4 in each one, which you can do on your calculator and get. And then that's going to give me 16 total ways to get 3 kings and 1 queen. So my probability is a little higher on that one. Not by much. Okay. See, these do get a little harder. Okay, a lot harder. Let me show you a couple more. Okay. I have to show you the work on 2 at a time, whatever, it doesn't matter. Number 9, 2 kings, 2 queens. Well, you have 4 kings and you're choosing 2, 4 kings and you're choosing 2. And so you do your combination there, you should get 6. So where am I getting that from again? I'm going 4, math, probability, oops, I went 1 too many, down to combination, choose 2, that's 6. 4, choose 2. So 6 times 6 is 36. And so you have 36 out of all of those. All right. What about getting no kings? I'm going to skip this side because they're basically the same thing. If I don't want any kings, then that leaves me 48 cards to choose 4 from. So that's going to be a big old number. So that's a way higher probability to get no kings because there's only 4 kings in the whole deck. Okay, so that was using combinations. Let's see. I think I had another one with, I wanted to show if I can find it. I have all these different papers everywhere. I thought I had a couple more that people these are all straight from your homework, most of them. Okay, if a family with 4 children, what's the probability of having 2 girls and 2 boys? Okay, so sample space. The sample space will be, you have 2 options times 2 options times 2 options times 2. You could also make a tree diagram for something like this. It would go boy, girl, just like our heads, tails, and then off each of those, boy, girl, off each of those, boy, girl. And there would end up with 16 at the end of your tree, okay? And this is asking, and then you could look specifically at your tree and see which branches and count them. Do you have 2 boys and 2 girls? Or you could think there's 4 total, and I want to choose 2 boys or 2 girls. So there's 6 ways to choose 2. Okay, so it's 6/16. So that one's a little different. I didn't times them. I don't have an or well, I do have an and. Yeah, I can't think of another way to make sure you get the 6/16. Yeah, the only other way I could think of is if we did the tree, which would just be girl, boy, 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 girl, boy. Ooh, man, there's a bunch of them. All right, girl, boy, girl, boy, girl, boy, girl, boy, girl, boy, girl, boy. Those ones are kind of blended there. This one too, girl, boy, boy, girl, boy. So then you just count the ones that have two of each. So not this row and not this row, because I only had one. Two girls, boy, boy. Right here. Here's one. Okay. Girl, boy, girl, boy. Ooh, there's another. Girl, boy, boy, girl. There's another. And then over here, boy, girl, girl, girl. No, boy, girl, girl, boy. Ooh, yeah. Boy, girl, yep. That one. Boy, girl, boy, boy. No. Boy, 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 boy. No. Boy, girl. Boy, boy, girl, girl. I already did. Did I miss one? No. Boy, girl, boy, girl. Thought I missed one. Boy, girl, 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 boy. Boy, boy, girl, girl. There it is. Whoop. How many are there? 1, 2, 3, 4, 5, 6. There are 6 out of 16 total. I like drawing stuff. It takes time, but these can get confusing on what it's talking about. So don't be embarrassed to do things like girl, girl, boy, boy, and then do all the different combinations or a tree diagram. Anything that will help you think of those. I love this oops, I wrote on the back of something. Oh, well. I love this Powerball question here. So the Powerball has 1 through 69, totally true. White balls with five choose. I did not word that right. And 1 through 26 red balls with 1 chosen, with 5 balls chosen. I just don't have an in. What is the probability that you'll match all these numbers and win? All right, so what's our sample space? So our sample space for the first one, we have 69 balls and we're choosing 5. For the second one, we have 26 balls and we choose 1. We have to times those to get our total sample space. Whoo, big number. As that's what we do when we get total numbers of things. We times them. And I think you did that before in the other section. Now, for the top number, we're going to pick 6 total balls out of all those combinations. Oh my goodness, that's so small. So small. So I just said this is the number, 0.000. This is for the percent, moving it 2 places. Not very likely to win the Powerball. All right, so there's more examples in your in the textbook, you know, the canned examples too. So let me just show one probability chart for you. So this is the probability when you roll 2 dice and you add the numbers. So you roll 2 dice and add the numbers. I could get a 2 with the 1 and the 1. I could get a 3 with 2, 1 or 1 and 2, so forth. So you can see there's 1 out of 36 because 6 times 6 is 36. So we have 16 or 36 total ways to get a result from dice. And again, you could draw a tree diagram. It's pretty big because it has 36 branches, but you could see there's one combination for this number, and then it goes up, 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 with 7 having the highest probability and then back down. Okay, so that's just a probability chart. these numbers better add to the number 1, meaning there's 36 ways, there better be 36 represented on the top for a probability chart to be fully completed. All right, so basic probability, hopefully you're able to get through that. Every problem looks different, so it'll just take you some time to get used to that. All right, good luck.